In the last section involving graphing polynomial functions, we found x-intercepts by setting the polynomial equal to 0, and we solved that resulting equation by factoring. Sometimes, however, you cannot factor a higher degree polynomial function using the greatest common factor or factoring by grouping. There are some polynomials that we're going to have to factor in a different way. Before we actually get there, we're going to have a background section 4.2, zeros by synthetic division, to prepare for those polynomials that we cannot factor directly. Synthetic division is basically a shortcut for long division. Now, if you are familiar with the long division of real numbers, the long division process for polynomials is very similar. Notice in the example of real numbers, we have 104 divided by 3. This part is what we call the dividend. This part is the divisor. This is the quotient. And this little guy is the remainder. Now, oftentimes when we're working with division, we can express the result as a mixed fraction. We take the quotient and we add the remainder over the divisor. So this would be the same thing as 34 and 2/3. We obtain the same pattern with polynomial long division. We have a dividend, a divisor, a quotient, and a remainder. So when we express the result, we do it the same way we do with real numbers. That is, we take the quotient and we add the remainder over the divisor. We follow that same pattern. So we take the quotient, we add remainder over divisor. Now, if that looks a little bit intimidating to you, I have some great news. We're going to learn the synthetic division procedure. Synthetic division is a shortcut process for the polynomial long division that you see here in this example. So I wanted to write this over here so you would appreciate this shortcut process called synthetic division. Synthetic division is an efficient process, think shortcut, for dividing a polynomial by a binomial of the form x minus k. So let me teach you the synthetic division process. And it is a very simple shortcut process to polynomial long division. Example 1, use synthetic division to divide 2x cubed minus 4x squared plus 5x minus 7 divided by x minus 3. Remember, we treat that fraction bar as the division operation. So the way we set up synthetic division, we create a little box out here. And we're going to put the 0 of the denominator in that box. So look at the denominator. The denominator is x minus 3. If I set that equal to 0 and solve for x, I would get 3. So this space is for the 0 of the denominator. That's going to represent basically the divisor that we have over here. Now, then, on the next line, we're going to record the coefficients of the polynomial. So we have 2x cubed minus 4x squared plus 5x minus 7. So I'm leaving all the variables behind and just picking up the coefficients of the numerator, or the coefficients of the dividend. Then I'm going to skip a line and draw a baseline. And the first step in synthetic division is to bring down that first number 2. Then we're going to follow the pattern of multiplication and addition all the way across this table. Here's what I mean. We're going to take 3 and multiply it by 2 to get 6, and that's going to go in this spot right here. Then we're going to add those two numbers together to get 2. Then we're going to multiply and add again. This time 3 times 2, that gives me 6 again. And then I'm going to add vertically. 5 plus 6 gives me 11. We're going to do one more round. 3 times 11 is 33. That number goes over here. And then I'm going to add vertically. Negative 7 plus 33 is 26. So notice this line right here represents the dividend. This box represents our divisor. So this part is the quotient. I just have to learn how to interpret it. And very importantly, anything in this last spot is the remainder. So here's how we interpret our answer. We started out with a degree 3 polynomial, right? The degree of the numerator was 3. We divided by a degree 1 polynomial. So the result, which is represented here on this baseline, should be 1 degree less than the original. So if I start out with degree 3, the result is going to be degree 2. So what I'm going to do is take the coefficients on the last line of my synthetic division problem, and I'm going to assign descending powers of x starting with degree 2, or x squared. So we have 2x squared plus, the next term would be 2 times x, plus that would be my constant term. The last spot on that baseline is the remainder, and so just like we do with real number long division, we express it as a quotient with the original divisor. So look at this result and compare it to the result of polynomial long division. Notice we get exactly the same thing, but the synthetic division process is fast and efficient and simple, whereas polynomial long division is a little bit more involved. Again, you do not have to know polynomial long division, but do appreciate the synthetic division process in the fact that it replaces a longer process. Okay, let's try that again. Our goal in this section is to make sure we know this synthetic division process because it's going to help us factor later on. So let's go ahead and set up our synthetic division process for example B. Remember, in this little box, we record the 0 of the denominator. The 0 of the denominator here is 2. Notice I'm just changing the sign of this number as a shortcut in the denominator. Then, in the numerator, we're going to record the coefficients of x from the numerator. So we have 1x to the 6th minus 2x to the 5th, and we're just going to continue this process. However, we have a little bit of a problem on this one. Notice the quotient, or the dividend in the numerator is missing a power of x. We're going to insert a 0 as a placeholder for that missing power of x. So we're going to have 0x cubed, then we're going to have negative 10x squared. Also notice the x power is missing, so I'm going to have a placeholder for that power, and then negative 35. Now let me explain that again. Make sure you understand what I'm doing. I'm going to go back up here to my real number long division example, and I want to look at this 0 right here. In the number 104, we know that this means we have 1 100, we have 0 tens, and we have 4 ones. Remember the days of elementary school and you're learning about place value? If I have a 0 right there, that means 0 tens. Now, with real numbers, I can't just say, well, it's 0, I'll just delete it and write that number. 104 and 14 are not the same number. That 0 in 104 is an essential placeholder. In the same respect, when we use synthetic division, we have to have a placeholder for every descending power of x. And by descending power, we're going to start with the highest power, make sure we have a representative of every power down to the last term. So look at our powers. 6, 5, 4, 3 is missing. 2 and power 1 is missing, and then we have our constant term. So these zeros are placeholders for those missing powers. It's very easy to overlook that and to forget that, but if you do not have those zeros, you won't end up with the right answer. Okay, let's go through our process. So we bring that first number down, and then we're going to take the number in the box and multiply it by the number on the baseline. 2 times 1 gives me 1. I put the result right here. And then we add vertically. Negative 2 plus 1 gives me negative 1. And then we'll repeat that process all the way across. 2 times negative 1 is negative 2. Then we add vertically to get 3. We're going to multiply the number in the box times the number on the baseline. 2 times 3 gives me 6. Add vertically, 0 plus 6 is 6. Continuing, 2 times 6 is 12. And then add vertically, negative 10 plus 12 is 2. Are you getting the hang of it? It's a pretty simple process. multiply, add, multiply, add. Negative 35 plus 8 gives us 27. Okay, so that process is done. And by the way, if you did this with polynomial long division, you would have an enormous problem. Now, let's interpret our result. This line represented a degree 6 polynomial, right? I'm looking at the highest exponent there. So the result is always 1 degree less. This is going to be degree 5. So that indicates that I should start assigning powers beginning with x to the 5th. So picking up our first coefficient here, we're going to have 1x to the 5th. The next power down, 1x to the 4th, plus 3x cubed, plus 6x squared, plus 2x, plus 4. Now remember, that last spot is always the remainder. So the proper way to express it, we're going to add the remainder over the original divisor, x minus 2. And that is the result of our polynomial long division. Now, it's simpler to write it without the coefficient 1. If they're there, it's not incorrect. It's usually just a little more readable without those values. So we have a quick, efficient, easy process for replacing polynomial long division. Again, this is going to help us to factor in the next section. But remember those placeholders. Those are very important. Be watching and looking for those. Okay, let's try the next one. X to the 5th plus 1 divided by x plus 1. Looks like a relatively simple problem. In the box, we're going to put the 0 of the denominator, which in this case is negative 1. Then we're going to record the coefficients of the numerator on this first line. We have 1x to the 5th. Do you notice we have a lot of missing powers here? 0x to the 4th, 0x cubed, 0x squared, 0x, and finally our constant term. Now, to keep up with all that stuff, it is a-okay if you want to list your powers up here to make sure that you have, and I'll put a C there for constant, to make sure you have a placeholder for everyone. Skip a line, bring down that first term, and then multiply the number on the baseline times the number in the box, and then add vertically. Okay, next, number on the baseline times the number in the box, we get positive 1. 0 plus 1 is 1. Multiply here to get negative 1. Add vertically to get negative 1. We're going to see a repeating pattern here. Notice in this case, our remainder is 0. So we end up with, let's see, we started with a degree 5 polynomial. Remember the rules of synthetic division. This is always 1 degree less than the original. So we can go ahead and express our result starting with x to the 4th. We have 1x to the 4th minus 1x cubed plus 1x squared minus 1x plus 1. And there's no remainder, so this came out perfectly. Now let me ask you a question. If I gave you the polynomial x to the 5th plus 1, and I asked you the question, is x plus 1 a factor of x to the 5th plus 1, would you know the answer? Maybe you do, maybe you don't. If you don't, let me ask you this question. Is 2 a factor of 10? I hope that you said yes. How do you know? Well, if I take 10 and I divide it by 2, I get 5. It comes out evenly, right? There's no remainder. So back to the previous question, we can say yes, x plus 1 is a factor of x to the 5th plus 1 because when we divided it out, we got a 0 remainder. And that's sort of the context that we'll be using this synthetic division to factor more complicated polynomials coming up soon. Let's do one more example for this video. Remember, in the box, we put the 0 of the denominator. So should I put a 2 or a negative 2 in the box? Hopefully you said negative 2. Let's check for all the powers. 4, 3, 2, 1, and then constant term. Looks like everybody's present and accounted for, so all I have to do is pick up coefficients. 1, negative 3, negative 11, 5, and 17. Skip a line, bring down that first term. Then we're going to take the number in the box times the number on the baseline and multiply them together, and then add vertically. Okay, next, negative 2 times negative 5 is positive 10, and negative 11 plus 10 is negative 1. Negative 2 times negative 1 is positive 2, and 5 plus 2 is 7. Next, negative 2 times 7 is negative 14, and 17 minus 14 is 3. So I'm putting the dots there just so you can kind of keep up with where I'm looking, which, whoops, losing my problem here. What did we have here? I think it looked like that. Okay, let's interpret our result. We started out with degree 4, so this must be degree 3, and do notice it did not come out evenly. We do have a remainder. So let's express our solution. 1x cubed minus 5x squared minus x plus 7, and then the 3 is the remainder, so we'll put it as a fraction over that original divisor. Let me ask you a question on this one. Is x plus 2 a factor of that big polynomial in the numerator? Hopefully you can recognize the answer. The answer is no, because when I take that polynomial and I divide it by x plus 2, the factor in question, we end up with a remainder. So the division did not come out evenly. That means if I'm going to try to factor this big polynomial, at least I can rule out x plus 2 as a factor. All right, synthetic division is pretty straightforward, fast and easy, and we'll be using it quite a bit. I bet your homework will go pretty fast for this section.